Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at trends in entropy. So this is more or less going to be how you can increase the entropy of a system, without letting a kid loose. So one of the big things to remember about entropies is that substances prefer to have more configurations or higher entropies. However, if I want to get an idea of what is more or less favorable for a system, I have to go ahead and be able to compare these entropies. So doing this, we're going to make use of three useful properties. First, note that Boltzmann constant is positive, and so will the number of microstates. And any natural log will always generate a positive number. And as a result, the entropy of a system is always positive, meaning that the system will always have some disorder present. Second is that entropy is a state function, which means if I know the final entropy and the initial entropy of a change, no matter what kind of change it is, whether it's a reaction, a temperature change, a phase change, doesn't matter. All I need to know is final and initial, and I've got my entropy change. Third is going to be the fact that entropy will increase if a system can adopt more configuration. So this is, again, that idea of those microstates. If there's more different possible ways I can arrange a system, microstates goes up, and then so does entropy. So classic example of how we increase entropy is going to be phase changes. So if I go from a solid, this is going to be a very well-ordered system. And then as I melt, I'm going to disorder this nice, beautiful crystal lattice we were talking about, and I'm going to make a slightly more disorganized liquid. That is the very nature of how you go from solid to liquid. You increase the entropy. So with very, very few exceptions, entropy of melting will always be a positive change as I go from solid to liquid. Similarly, a liquid is still relatively condensed, relatively ordered, and it doesn't really get more disordered than a vapor. We've got small particles moving around in big open spaces, and remember, bigger is better, with lots of possible arrangements. So the entropy of a gas is going to be huge because we're going to have a big increase of the number of configurations with each of these phase changes. And if you go ahead and use water as an example, you'll really see kind of the order of magnitudes here. So at room temperature, solid water or ice has a decent entropy. It almost doubles by the time you go to a liquid, and that more than doubles as we go to a gas. So we do tend to see very big changes. So in general, one of the big things that's worth noting is the entropy of a gas is always going to be much greater than the entropy of a liquid, which is greater than the entropy of a solid. So again, fusion, good entropies involved, but it will never really compare to the entropy of vaporization. Other important things to make note of is if we're comparing different substances. So generally, as a substance becomes heavier, we're going to have a higher entropy. And one of the big reasons why is that as a substance gets heavier, it has far less to do with the number of protons or its mass. It has much more to do with the number of electrons. So for example, if I was going to look at two different isotopes of the same system, really entropies won't differ that much. But if I go from fluorine to chlorine, where suddenly I now have introduced an extra 16 electrons, 8 on each atom, we see a fairly significant change in the entropy. So as we get more electrons able to move around and interact, we will see an increase of entropy. But do note this is nothing even on the same order as a phase change. So this is kind of a secondary feature. Similarly, you also tend to see entropies go up as you go from small molecules to larger molecules. So if I go from methane, which only has 4 atoms, to ethane, which now has 8, so double the atoms, and I see a decent increase in the entropy of the system by about 40 joules per mole each time I add that extra 4 atoms. However, note that this will be greater than just adding electrons, but unless you do a big jump, such as methane to propane, really, again, not quite on the order of phase changes. So this gives us kind of an idea of what is more or less important. However, one of the things I do like to emphasize is that, yes, we do see a decent increase of entropy as I go from methane to ethane. However, if I'm looking at the entropy per atom, generally it's going to decrease. So each molecule has more entropy. However, in general, we'd expect big molecules, if entropy was in control, to fall apart. Thankfully, it isn't quite as much, quite that simple, as we'll talk about later in the chapter. So the next big thing that is also important when you're figuring out which molecules have more or less entropy is the important role of flexibility. So let's go ahead and take cyclopentane and pentene. So both of these have the same number of carbon atoms and the same number of hydrogen atoms. Biggest difference, cyclopentane forms a ring, cyclopentene doesn't. And so as a result, it turns out the cyclopentene has a lot more flexibility, because one of the things that comes in play is that if you have an sp3 carbon and most sp3 atoms, this means that the system can go ahead and freely rotate. So this is an example of pentene. This is a configuration of pentene, and this is a configuration of pentene. And if I go ahead and I have pentene in solution, all three of these plus dozens of more will all be present. If you have a ring, well, that ring really can't flex nearly as much. And as a result, if you go ahead and compare these two molecules, it isn't too surprising that the one with a higher flexibility has a higher entropy. One of the things you should, again, make sure to note, if you see a ring or a double bond, this removes flexibility of the system, because in the case of a ring, well, I can't exactly, flex a ring the same way I could flex a straight line. In terms of the double bonds, this is because essentially I have those fixed p orbitals, which always have to stay in the same place, and that prevents nearly as much flexibility and rotation. So we won't spend that much time on the flexibility of a molecule here. However, if you do go on to organic chemistry, this will come into a lot of play with the behavior of many common molecules. Finally, the last major form of trend of how we can increase or decrease entropy is by looking at temperature. Because remember, as I have higher temperatures, I have essentially more energy in the system. And it isn't too surprising if I add more energy into the system through the form of heat, my temperature will go up and I should get more entropy. However, it turns out that this is going to be dependent upon what my initial temperature is. And so this can often be said that change in entropy will be related to the heat capacity, so how much energy it takes to raise the temperature, and again, the change in temperature itself. So again, it is worth noting this is a calculus description, and you can use calculus to relate this as an actual discrete change in entropy. It turns out if you go ahead and do some fun integrals, you can actually express the change in entropy, again, as a heat capacity. Most commonly, we're going to be using constant pressure heat capacities, and the natural log of the ratio of the final and initial temperatures. And again, this comes from that dt over t. Now, the big thing that I really like to emphasize here is that when we are dealing with enthalpy, increased as the change in temperature. So if the temperature went up by 10 degrees, it didn't matter what my starting condition was, my enthalpy would go up the same amount. Not quite the same thing with entropy, because it depends on the ratio of final and initial temperatures, which means if I start at an initial temperature of 10 Kelvin and I increase 10 degrees, well, I doubled the temperature, so I'm going to see a big increase in entropy, which again makes sense because if I'm at a low temperature, the system is very highly ordered. So if I see a doubling of temperature, I should have a big increase in the number of available states. I should probably double it. However, if I start at 1,000 degrees, well, adding 10 extra, increasing the temperature by 10 really doesn't make a big difference. And so as a result, I don't have that many different additional ways I can rearrange the configurations. And so we're going to be using a lot of these basic trends to figure out what happens to the entropy as I go from, instead of simple processes like heating or cooling or phase changes, to big chemical reactions. So next time, we're going to focus on the entropy of a chemical reaction. Until then, Take care.